Welcome to the Deep Dive. We sift through stacks of info to pull out the really crucial insights for you. Today, we're diving into a pretty big shift that's happening in AI engineering.
Yeah, it's interesting. For the last few years, it feels like a lot of AI apps were built, leaning heavily on these big model APIs, OpenAI, Anthropic, DeepSeek, those guys.
Right, and that API approach, it creates a boundary, which is good, right? It helps manage the complexity. You don't need to know exactly how every little piece works underneath.
Exactly. Keeps things from getting totally overwhelming. But like you said, things are changing. That boundary is becoming, well, maybe a bit more permeable, or at least we need to look past it more often.
Okay, so that boundary was useful, kept things abstract, but it also kind of shielded AI engineers from the hardware, didn't it? So now you're saying if I'm an AI engineer, I suddenly need to care about GPUs in a much more direct way.
That's the gist of it, yeah. It's actually pretty similar to how developers use databases.
Ah, okay. How so?
Well, think about it. Most developers aren't writing the actual database engine code, right? And often they're not even running the database server themselves. They're using something managed, like AWS RDS or whatever.
Sure. But they absolutely have to know how to use it well, like how to write efficient SQL queries, how to make sure they're hitting the indexes correctly.
Precisely. There's that classic resource, use the index, Luke. The whole point isn't to teach you how to build a B tree from scratch. It's about making sure your queries use the index effectively so things run fast.
Gotcha. So you're saying we're reaching that point with AI and GPUs. You don't need to build a GPU, but you need to know how to use the index, so to speak.
Exactly. And that's kind of our mission for this deep dive. Why is this shift happening, and what specifically about GPUs does an AI engineer need to grasp to use this tool effectively now? And if there's one mantra we want you to take away, it's got to be use the tensor cores, Luke.
Use the tensor cores, Luke. Okay, I like it. So let's start with the why. Why this move away from just hitting APIs? What's this new frontier?
The big driver is really the growing maturity of open weight models. And coupled with that, the open source software to actually run them efficiently, things like Dynamo and VLLM.
So running your own models is becoming more realistic.
More than realistic, it's becoming economically sensible, even advantageous for a lot of use cases. Tighter integration, maybe better cost, more control.
Okay, so that ties back to the database analogy. Just like learning to use the index, Luke, unlocks database performance.
You got it. The ability to run your own models means you need to understand the hardware, the GPU, to make sure you're actually using its most powerful parts efficiently. It's about writing AI code that's, sympathetic to the underlying silicon.
All right, that makes sense. That's the why. So let's get into the what. What are the key things about GPUs that engineers need to get their heads around? You mentioned bandwidth versus latency first.
Yeah, that's fundamental. The absolute core difference between GPUs and TPUs too, compared to most hardware you usually program like CPUs, is this massive emphasis on high bandwidth over achieving low latency.
And latency. You're saying improvements there have kind of stalled.
Stalled is putting it mildly. I mean, the big leaps in reducing latency, that whole trend basically, died during the Bush administration, as someone colorfully put it. It's not coming back in the way it used to.
Wow, okay, so we can't just rely on things getting faster by themselves anymore. How did we get here? I remember when just getting a faster processor made everything quicker.
Oh, yeah, absolutely. Think way back, like the ZUSA-1 in the 1930s mechanical logic gates driven by a clock tick. Every tick, one operation. Fast forward to the 90s, you just cranked up the clock speed.
And boom, faster computer. No software changes needed.
Exactly. Nobody had to recompile, rewrite code, nothing. It just worked. But that free lunch, that just making the clock faster, it completely fell off a cliff in the early 2000s. Physics caught up. Heat. Power limits.
So for the last couple of decades, software has had to adapt.
Profoundly. We had to find other ways to get performance.
Okay, so if clock speed isn't the magic bullet, what are the strategies now?
Two main ones really dominate, especially in GPUs. First is parallelism, just doing lots and lots of things at the exact same time within one clock cycle.
And GPUs are way better at this than CPUs.
Oh, massively.
Yeah.
Like an AMD EPYC CPU might handle, say, 2 threads per core, maybe uses a watt per thread, roughly. An NVIDIA H100 GPU, the big ones, we're talking over 16,000 parallel threads.
16,000?
Yep, and maybe at 5 cents of power per thread. And the critical part is all 16,000 of those threads make progress simultaneously, every single clock cycle. It's just a different beast entirely.
That's an astonishing difference.
Cool.
Okay, so parallelism is one. What's the second strategy?
The second is concurrency. This is more about keeping busy pipelines full by starting new tasks before the old ones are completely finished.
Okay, and how do CPUs and GPUs compare there?
Well, CPUs look like they can handle tons of concurrent threads, in the operating system. But switching between those threads, the context switch, it's actually pretty slow, like maybe a microsecond, which is easily 1,000 clock cycles.
1,000 cycles just to switch tasks.
Right.
Ouch.
Yeah. So that limits true fine-grained concurrency. GPUs, though, they do context switching right down in the hardware at the level of the warp scheduler, basically every clock cycle. It's incredibly fast and efficient.
So parallelism and concurrency are the keys,
Mm-hmm.
driven by this need to leverage bandwidth. Is there, like, a rule or law that captures this?
There is. David Patterson, RSC pioneer, worked on TPUs. He described it really well. I kind of call it Patterson's law. Latency lags bandwidth.
Latency lags bandwidth.
Meaning if you look historically across different computer parts networks, memory storage bandwidth tends to improve much, much faster than latency. It's often like the square of the latency improvement.
The square, so a 10x better latency gives 100x better bandwidth.
Roughly, yeah. Think about it. Latency is often limited by physics. Speed of light for a network packet, We send data at maybe 70% of light speed through fiber. You can't really bribe physics to go faster. But bandwidth, you can just add more fibers.
Yeah.
Or make the channel wider. You can do more things in parallel using the same underlying physics. So the trend is clear. Bet on the hardware that scales bandwidth.
Bet on the bandwidth hardware. Got it. So for GPUs, that means leveraging their high bandwidth memory, like that fancy HBM stuff.
Well, yes, the memory bandwidth is high, much higher than CPUs. They use that stacked Hynix high bandwidth memory. It's impressive stuff. But here's the kicker. That's not even their main strength.
Oh, what is that?
It's the computation they can do on the data once it's loaded. It's the arithmetic bandwidth, not just the memory bandwidth.
Arithmetic bandwidth, you mean calculations per second?
Exactly. We talk about arithmetic intensity. The idea is, how many calculations can you perform for every byte of data you move from memory? GPUs are designed to do a ton of math, like n-squared operations for every n bytes you load.
So you want to load data once and then just crunch it like crazy.
Precisely. If you look at GPU performance charts, those huge numbers, the really big ones, often colored purple in NVIDIA's diagrams, that's the computational throughput. It vastly outstrips the memory bandwidth figures, which honestly haven't grown as dramatically.
Okay, that makes sense. It feels a bit like old school programming where you really had to minimize memory access.
It really does, yeah. You load stuff into registers or shared memory and then just hammer on it with calculations. This becomes super clear when you look at how large language models run, especially during inference.
Okay, walk me through that. LLM inference on a GPU.
Right. So take the first part, processing the prompt. Let's say you have an 8 billion parameter model, maybe using FP8, which is like a lower precision number format to save space and speed things up.
Okay.
You load maybe 8 gigabytes of weights from the main GPU memory into the compute unit's registers. Then you perform, I don't know, roughly 60 billion calculations, floating point operations. This part actually scales pretty well. It doesn't depend too much on how long your prompt is.
Sounds efficient enough. But I sense a but coming.
There's always a but. The problem hits during the next phase. Decoding. Generating the response, token by token, for each new token you generate.
Oh.
You essentially have to move those 8 billion parameters, those 8 gigabytes of weights, all over again from memory to do the calculations for that single next token.
Every single token. That sounds bad.
It is. It becomes massively memory bandwidth bound. You spend way more time fetching weights than actually computing. It's the classic memory bottleneck throttling your performance.
Right. So if decoding is stuck waiting for memory, what's the fix? How do you optimize? You said more computation. That sounds backwards.
I know, it sounds weird. But it fits the hardware strength. Remember arithmetic intensity. If moving memory is the bottleneck, do more math each time you do move it.
How?
Okay, here's a concrete strategy. Take a smaller model, maybe that Llama 3.8D we mentioned, run it, say, 1,000 times on the same prompt.
1,000 times.
Yeah. The weights, they only get loaded from slow memory once at the beginning, but now you're generating maybe 10,000 possible outcomes or sequences. You're doing vastly more computation relative to that initial memory load.
Okay. But then you have 1,000 outputs. What good is that?
Well, then you need a good way to pick the best one. Maybe you have a verifier, like a simple Python test or some criteria that checks which output is actually good or correct.
And does this actually work? Like, in practice?
It absolutely does. This isn't just theory, it's a legitimate research result that's been reproduced. People have shown you can take a model like Llama 3.8b, run it maybe 100 times like this, and get results that match the quality of a much, much larger model like GPT-4o.
Wow, so the smaller model plus massive computation can equal a bigger model's quality.
Exactly. It shows how these smaller models can be designed to be more sympathetic to the hardware, leveraging that computational power to overcome the memory bandwidth limits.
That's fascinating. Okay, which leads us neatly into the third key thing engineers need to know, focusing on low-precision matrix multiplications.
Right, because it turns out some operations on modern GPUs become almost, well, approximately free, as some people say.
Free compute. Sign me up. What kind of operations?
Things like predicting multiple tokens ahead instead of just one, or generating multiple samples at once, like we just discussed.
And why are these things nearly free? What's the magic?
The magic has a name: Tensor cores. These are specialized hardware units built into recent NVIDIA GPUs, and other vendors have equivalents. They do one thing, and they do it incredibly well: matrix multiplication, especially with lower precision numbers like FP16 or INT8.
So they're not general purpose like the other CUDA cores.
Nope. CUDA cores handle all sorts of parallel tasks. Tensor cores, they are hyper-optimized for matrix math, and that's where the absolute peak computational throughput comes from those giant purple numbers on the spec sheets. They blow the regular CUDA core performance out of the water for these specific tasks.
Okay, so tensor cores love matrix multiplication. How does that connect to LLM generation? You said that was memory bound and it involved moving parameters.
Right. The basic naive token-by-token generation often looks more like a series of matrix vector operations. You multiply the big weight matrix by the current state vector.
Which isn't the sweet spot for tensor cores.
Exactly.
Yeah.
But anything you can do to rephrase the problem to sort of upgrade that matrix vector work into a larger matrix operation, that becomes incredibly efficient.
How so? What happens?
Microbenchmarks show this clearly. If you feed a tensor core a big matrix and then another matrix that's mostly empty except for one column full of data, which is effectively a matrix vector, multiply the performance kind of tanks. It might drop to like 1/3 of the peak where n is the matrix dimension.
So it's starved for work.
Pretty much. But if you start filling up those other columns in the second matrix, maybe by calculating multiple tokens ahead or processing multiple sequences in parallel, suddenly you're doing a proper matrix multiply. And the performance shoots right back up towards that peak theoretical limit. You're keeping the tensor cores fed.
Ah, okay. So you're amortizing the cost of loading the big weight matrix over more useful computation.
That's a great way to put it.
So what does this mean practically for an AI engineer designing systems?
It strongly encourages these strategies we're seeing emerge. Generate multiple candidate tokens at each step, like DeepSeek does, or generate multiple independent samples like we discussed for boosting quality. Even the upcoming Llama 4 models are rumored to lean into this.
So you might not need the absolute biggest model if you can run a smaller one much faster and generate mini samples.
Precisely. You could potentially run a smaller model that fits comfortably on, say, a reasonably priced desk-side GPU, but then use these techniques, multi-sample generation, to scale up the quality and performance to match something much larger and more expensive to run. This whole area was actually a pretty active academic field right around when ChatGPT launched, and now it's becoming super relevant again because the base open models are getting so good.
Fascinating. Okay, let's try and wrap this up. To recap the key takeaways for you, the AI engineer listening. First, recognize that you can't just live behind API boundaries forever. Hardware awareness, specifically GPU awareness, is increasingly vital.
Second, internalize that GPUs are built for bandwidth, not low latency. Latency improvements stalled ages ago. Focus on techniques that exploit parallelism and concurrency.
Third, prioritize arithmetic intensity. Don't just move data. Calculate intensely on the data you've loaded. Minimize memory movement relative to computation.
And finally, understand the power of specialized hardware like tensor cores. Structure your computations, especially in LLMs, to use low-precision matrix multiplications whenever possible. That's how you unlock that peak performance. Remember the mantra.
Use the tensor cores, Luke. Got it. And if people want to dig even deeper into all the GPU jargon.
Yeah, there's a really helpful resource someone put together called the GPU Glossary. It's at modal.com/GPU-glossary. It aims to be like CUD docs for humans, explaining terms like warp schedulers, streaming multiprocessors, all that stuff, in a more accessible way, designed so you can just click through when you hit a term you don't know.
Excellent. Okay, so let's end with a thought to chew on.
Yeah.
Given everything we've discussed, this fundamental shift towards hardware that scales via bandwidth, computational intensity, and these specialized tensor cores, here's the question for you. How might this profound change in how computing scales actually reshape the types of AI applications we build, and maybe even the fundamental problems we choose to tackle in the near future?
That's a big question, something to definitely think about.